Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing the coordination chemistry of 3D elements. Last time we have seen the general characteristics of transition elements. In continuation with this point, today we are going to see the next part, that is some physical characteristics of transition elements in general. The first point of this topic is abundance. So if we see about the abundance, it is found that there is some law which states that the elements with even atomic number are most abundant. Elements with even atomic number are more abundant. It means the elements with all atomic numbers are less abundant. In addition to this, if we found that if we consider the abundance along or down the group, it is found that when we move down the group, say this is, if any group, it is 3 to 12, then we found that as we move down the group, the abundance decreases. Abundance decrease. For example, if we have this scandium, yttrium and lanthanum, then the abundance is found to be decreasing in this direction. Means scandium, the elements of 3D groups are most abundant in this case. Then next is yttrium, next is the lanthanum. Then it is found that the elements such as RH, Ru, that is ruthenium, rhodium, RH, rhodium, then palladium, silver, gold, platinum, etc. are very rare elements. Their abundance is much less than 0.15 ppm, that is parts per million. Then next point is size. Size of the atoms or ions. We assume we consider the size of the atoms or ions as their covalent or ionic radii. Now, it is found that the covalent radii are decreasing from from group 3 to 12. This is because the electrons are added in the same d subshell. For example, in the 3D subshell, the electrons are added from 3D1 to 3D10, and during this the nuclear charge, means atomic number, that is and nuclear charge also increases in the same direction. And because of this nuclear charge, increasing nuclear charge, the electrons are held closer and closer, and that is why their covalent radii are found to be decreasing. Means the radius can be considered in different manner. So this is R means indicates the covalent radius, we can say Rn. For comparison, we can take the constant value of this R, N, that is oxidation state, say for example +3. Then the shielding of nuclear charge. So as we move from 3D to 10, 3D to 3D10, the nuclear charge increases, and this is shielded by these electrons. So nuclear charge is shielded continuously by here 1 electron, 2 electrons. So as we move from 3 to 12 group, the nuclear charge is found to be shielded more and more by every new added electron. And because of this, the lanthanide contraction is observed. For example, in case of this scandium, yttrium, lanthanum and actinium, we know that the electrons, there are 14 F elements. There are 14 F elements, and then next to it is hafnium. So the nuclear charge increases here, but the electrons are entering into the F substate, and hafnium is lying. This is third group, and hafnium is from fourth group. So between these two elements, 14 electrons are placed in the F substate, and next electron goes into the D substate, that is 3D2, 4D2 here. 4D means the 4, this not 4, the 5D here, it will begin with 5D series here. So the electron goes into this hafnium in the D substate, lying next to lanthanum but coming after 14 elements called lanthanides. And these lanthanides shows the contraction of the sides, and this is called the lanthanide contraction. Lanthanide contraction. So because of this, the elements coming after hafnium are showing more and more decrease in the size, and because of this, the size of this hafnium and element lying in the series of yttrium are coming very close to each other, and because of this, the elements from the upper series, say here 3D, 4D and 5D are having same size, and that is why such elements appear closely in the Earth's crust, and that is why their separation is more and more difficult. Then next is the variation in size. So we have seen that in case of these scandium, yttrium, lanthanum and actinium, the size varies with a very small magnitude. For example, if we consider the size, it shows that in case of scandium 3+, etc., if we consider the size in angstroms, it shows that The size of scandium 3 plus is 0.70, then yttrium 0.90, then lanthanum 1.06. Then again if we take next series to scandium, that is titanium 4 plus, then zirconium 4 plus, then hafnium 4 plus. The size is different. So you will find that 0.68 in angstrom, 0.74, 0.75. So if we see that the size of these three elements, as we have seen earlier, the size of the three elements is very close, and that is why they are appearing in the earth's crust or in minerals together. And some of these elements are called the twin elements because of their similar chemical properties and very small difference in their physical properties. So these things makes the separation of such rare earth elements more difficult. Then next point is melting points and boiling points. That is physical constants. Melting points and boiling points. In general, it is observed that the melting points and boiling points of alkali metals and alkaline earth metals are lower, but the transition metals have generally very high melting points and boiling points. But there are some exceptions like the 12th group elements, where the D subshell is, if we say group 3 to 12, the elements have here say D1 configuration, and here you will find the D10 configuration. So here configuration is electronic shells are completed, and therefore their melting points and boiling points are low. But here you will find that these elements will have high melting and boiling points. For example, zinc, cadmium and mercury have D10 configuration like this, and therefore their melting points and boiling points are lower. So these are some exceptions. Generally the lanthanum, silver and all other metals of these 3 to 12 group are having very high melting points above 1000 degrees centigrade. Comparatively, S block elements have much less or lower melting points. Lithium has 181 and cesium has 29 degrees centigrade. Then next point is density. The next point is density. So the group 1 to 2 atomic volumes means atomic volumes of S block. So that is group 1 and 2. The atomic volumes are large, and that is why their densities are very low. But the elements coming after this second group, that is group 3 to 12, the atomic volumes goes on decreasing, but the electrons are number of electrons goes on increasing. The nucleons, that is nuclear charge or contents of the nuclei, are also increasing, gradually. As a result of this, the density of these elements increases in this direction. For example, if we consider the elements such as osmium, for example, osmium has density 5.6 gram per cubic centimeter, that is cc. So in this way, these generally in all we can say the density of transition elements is high, and there are some exceptions, that is the first 3D group elements, that is scandium, yttrium and titanium, have relatively low densities. Then next point is reactivity. Next point is reactivity. The S block elements have very high reactivity because they have 1 or 2 electrons in their valence shell, and they have tendency to lose these electrons rapidly. As a result of this, they are very reactive. But the transition elements are relatively less reactive compared to S block and P block elements. This is because of the number of electrons which can be lost easily or rarely. Means the electrons present in these transition elements are not easily lost. Means they cannot be easily converted into the cations, and therefore their reactivity is found to be much less or very less. The heats of sublimation of these transition elements is also very high. Their heats of solvation is low, and they have, this is because of the small size of their atoms. Then ionization energy also indicates about the reactivity. Ionization energies of these transition elements are also very high, because of which their reactivity is very low. Then inertness becomes predominant in some of the transition elements like gold, silver, platinum, etc. Means because of their inertness, these elements are found in their elemental state or native state in the soil or in the nature. Then if we see the ionization energies of these elements, as we have seen that the ionization energies of these elements are very high, and compared to S and P block elements, it is found that in case of lanthanum, the ionization energy is relatively less. In case of lanthanum, the ionization energy is 541 kilojoules per mole, and in case of the mercury, this is 1007 kilojoules per mole. So in all, we can say that transition elements have very high ionization energies. So because of this, they may form ionic and covalent compounds. But there is also some difference. The lower oxidation states for ionic, or they are lower oxidation states are ionic, means they elements in lower oxidation states are ionic compounds, whereas higher oxidation states gives covalent compounds. So in this way, we can consider the possibility of formation of various ionic compounds or covalent compounds in comparison with their existing oxidation states. Then next point is color. If we see about the color of the S block elements and P block elements are found to be generally colorless. But transition metals and their transition elements give ionic and covalent compounds which are mostly colored. The exception is in case of the elements of 12th group, because the electrons are 10. So compounds of such the 12th group elements are found to be colorless, but the rest of the elements, that is D1 configuration to D9 configuration, the metal ions gives compounds which are colored. The color is always associated with the ability of the metal ion to excite the electron and promote that electron to a higher energy level. So the absorption of the radiation from the source, or you can say sunlight, is taking place in the visible region of the spectrum, as a result of which the compounds are exhibiting various colors. And here it is in case of these transition elements, the levels, say this is D level and this is another D level. So this is filled D level, filled, and this is vacant. So electrons are moving due to absorption of energy, that is H nu. So they can absorb radiations from the source, and when the electrons are excited to higher energy level, then they again come back to the ground state, during which the radiations are given out, and because of which the color of the substance is observed. And these are D levels. So this is also D level, this is also D level. Therefore it is called DD transition. So DD transition is responsible for exhibiting colors of the transition metal compounds. So if the blue color is shown by the compound, it means the compound absorbs the radiations corresponding to red color. So in this way, metal ions in their various compounds exhibit different colors such as blue, yellow, green, etc., or various combinations of these colors. But the compounds such as zinc sulfate and titanium, means if we take the compounds of say D1 configuration and D2 configuration, means that we say for example scandium and yttrium, then scandium and titanium, then we find that scandium 3 plus and titanium 4 plus, such as here you will find that they, for example TiO2 and the D10 configuration having zinc with the 2 plus state, that is zinc oxide, or zinc sulfate, we can say zinc oxide or zinc sulfate, we can take this example, are found to be colorless. They are colorless. Then next point is magnetic characters. magnetic characters. Magnetic characters also depend upon the presence of electrons in the unpaired state or in the paired state. If the substance contains electrons in the paired state, the magnetism is called a dimagnetism. Dimagnetism. Or the substance is called diamagnetic. If the substance contains unpaired electron, one or more, then it is called paramagnetic. It is called paramagnetic. So paramagnetism arises due to the presence of unpaired electrons, and diamagnetism arises due to the presence of paired electrons. Means when all electrons are in paired state, the substance becomes diamagnetic. When there is at least one electron in the unpaired state, it is called paramagnetic substance. The magnetism is considered in different elements. For example, if the elements such as iron, cobalt and nickel, they are strongly paramagnetic, means they give the magnetic magnetism called ferromagnetism, because of which they can produce, or these elements, metals, are used to produce permanent magnets or very strong magnets. The magnetic properties are determined using, means magnetic moment of the metals or substances can be calculated or we can say observed by using Guy-magnetic balance method. Here the sample is weighed and from this change in weight of their substance, by means using this experimental method, we can find the magnetic moment of the substance, that is mu. We can find the magnetic moment mu, and this magnetic moment is correlated with the number of unpaired electrons, that is n. So if we consider n as a number of unpaired electrons, then it is given as, this mu is given by the formula square root of n into n plus 2. N into n plus 2. So we can, by using magnetic balance method, diamagnetic method, we can get this mu in Bohr magneton, and from this we can find out these unpaired electrons by using this formula. Say, for example, if we are having this number of electrons, square root of, say here the number of electrons are 2, then we can calculate this 2 plus 2, means 2 into 4. So square root of 4 means 2 into 4 means square root of 8, and this gives the magnetic moment 2.83 in Bohr magneton. So if we find, by using Guy-magnetic balance method, if we find the magnetic moment close to this number, it indicates that the substance, means metal ion present in that substance, must contain the number of electrons 2, that is n must be equal to 2. Means in this way the Guy-magnetic balance method is used. Again, another example we can take. See, if the magnetic moment is 1.73, means that it may not be accurately that, it may be very close to that, and or if it is very close to or 1.73 Bohr magneton, it means the number of unpaired electrons present in the substance, that is metal ion, must be 1. Then next properties is catalytic properties. Catalytic properties. The catalytic behavior is exhibited because of the metals which are having variable oxidation states. This is important statement. The transition metals have variable oxidation states. What is meant by this? It means the metal ion can exhibit 1 or 2 or at least 2 or more oxidation states, and in such case the metal ion or the metal compounds can exhibit catalytic properties, because when the metal is reacting with some substance, it gives some intermediate product, and that intermediate product provides the surface area where the absorption of the reacting species takes place, and that surface is giving the acceleration means that absorption of the reacting species are accelerated to give the faster products very rapidly. So most of these transition metals are found to be having catalytic properties. For example, FeSO4 and H2O2. FeSO4 and H2O2 is a catalyst used for oxidation of alcohols. So it is used for oxidation of alcohols. Oxidation of alcohols into aldehyde. So this is called oxidation. So although alcohols can be easily oxidized by using this FeSO4 in presence of H2O2, so this acts as a catalyst. So we can have such different examples. For example, if we take Fe or MO, Fe or MO, molybdenum. So this is used in the manufacture of ammonia. Similarly, palladium is used in hydrogenation of oil. Hydrogenation means addition of hydrogen to convert the unsaturated organic compounds in the saturated organic compounds. For example, phenol is converted into cyclohexane. Means reduction is carried out of phenol, which gives the product cyclohexane. Then another is platinum rhodium. It is platinum and or rhodium. It is used in the oxidation of ammonia. It is used in the oxidation of ammonia to give nitric oxide. That is oxidation. So platinum and rhodium acts as a oxidizing agent. Similarly, vanadium pentoxide V2O5 is also used. V2O5 is used as a catalyst to convert sulfur dioxide gas into sulfur trioxide gas. The oxidation of this sulfur dioxide takes place. Similarly, titanium tetrachloride, TiCl4, TiCl4 is used as a Ziegler-Natta catalyst. Ziegler-Natta catalyst. So it is also used in polythene polymerization, in the formation of polythenes, that is in polymerization. In some reactions, the variable oxidation states are, some oxidation states are unstable, and it gives the intermediate product, and it provides the surface area for the absorption of the reacting species. Now, the next is variable oxidation states. Variable oxidation states. So here, if we find the 3D elements, so there are various elements in this 3D series, that is starting from scandium to zinc. So there are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So these elements shows variable oxidation states. So for example, scandium exhibits 2 and 3 plus 2 and plus 3 oxidation states. Similarly, here titanium exhibits oxidation states 2 and 4. So in this way, we are not going in much detail. We will show that as we go progressively in towards right side, the number of d electrons, so this is d1 to this d10. So this is in d1 case, there are this one, this is not one, the oxidation states are only 2 and 3 here. Titanium has 2 and 4. So as we move from d1 to d2, the number of oxidation states goes on increasing. As we move from d2 to d3, the number of oxidation states also increases. So in this case, the number of oxidation states are 2. Here the oxidation states are 3. Titanium has 3. If vanadium has again 4 oxidation states, vanadium has 4 oxidation states, 2, 3, 4, 5. 2, 3, 4, 5, like this. Chromium has 5 oxidation states. Chromium has 1, 2, 3, 4, 5, and 6. So in this way, manganese has Mn has also oxidation states 1, 2, 3, 4, 5, 6, and 7. Again, if we go to the, so here if we see the Fe, the oxidation states are 2, 3, 4, 5, 6. So in this way, the number of oxidation states are increasing in this way, like a pyramid. And again, after this manganese, the oxidation states are decreasing. So in this way, the cobalt exhibits 4 oxidation states, nickel exhibits 3 oxidation states, copper exhibits 2 oxidation states, and zinc exhibits 2 oxidation states, but out of which one oxidation state plus 1 is unstable. Only 2 plus state is stable. And then copper also exhibits 1, 2 and 3 oxidation states, out of which the oxidation state number 3 plus 3 is highly unstable. So in this way, the variable oxidation states are found in the 3D subshell. Similarly, there are variable oxidation states also in the 4D and 5D series. These metals, 4D metals, for example, molybdenum, gives metal-metal bonding in their complex species, such as MO6, Cl8 and Cl-4. So Cl minus is 4. So here you will find that this molybdenum shows metal-metal direct bonding. So it contains a cluster. It gives a cluster due to the bonding between the metal atoms. Similar to 3D series, the metals of this 4D series, that the yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium, also exhibits various oxidation states. Yttrium gives only 1 oxidation state plus 3, zirconium gives 3 oxidation states, 2 plus 2 plus 3 plus 4, niobium gives 2, 3, 4, 5 oxidation states, molybdenum gives 2, 3, 4, 5, 6 means plus oxidation states, technetium gives 1, 2 unstable, plus 2 is unstable, 3, 4, 5, 6, 7, ruthenium gives 2, 3, 4, 5, 6, 7, rhodium gives 1, 2, 3, 4, 5, 6 oxidation states, palladium gives 2 and 4 oxidation states, silver gives 1, 2, 3 and the cadmium gives 1 and 2, but 1 oxidation state plus 1 is unstable. Similarly, the lanthanide series, that is 4D series, also gives variable oxidation states, out of which lanthanum gives only 1 plus 3 oxidation states. Hafnium has 3 oxidation states, 2, 3 and 4. Tantalum has 4 oxidation states, 2, 3, 4, 5. Tungsten has 2, 3, 4, 5, 6. Rhenium has 1, 2, 3, 4, 5, 6, 7. Osmium has 2, 3, 4, 5, 6, 7, 8. Iridium has 1, 2, 3, 4, 5, 6. Platinum has 2, 4, 5 and 6. Gold has 1, 2, 3, 5, out of which plus 2 is unstable. And mercury has 1 and 2. So this mercury has exceptionally the plus 1 oxidation state. So in this, with this, we have completed this topic, and next time we will go to the next point, that is electroneutrality principle. So till then, see you next time. Please subscribe to this channel and press the like button and bell icon. So thank you very much for watching this video.